Hello guys, this is Numerical Cap, and today I'm going to talk about some non-minimal coupling effects which can be seen in cosmology, or what could be the effect of non-minimal coupling between dark matter and dark energy, and which can be observationally, can have some signature in cosmic evolution. So first of all, I'm going to start with current crisis in cosmology. As we understand it, there is some kind of crisis is happening with the model of lambda CDM. So we are going to shed light on current crisis in cosmology, and then we are introducing what is the interacting dark energy. It means that we have also talked about in this channel that there is some kind of dark energy and dark matter uh, are the constitution of this universe, and there could be some kind of interaction which is non-gravitational interaction can exist. So this is also called an interacting dark energy. So we are going to see in detail that what is not interacting dark energy, and then we are going to see that what is the dynamic system stability analysis. It's a wonderful mathematical framework, mathematical tool in which we can study any very complex equations and all these things in a qualitative manner. And then we are going to finally conclude this presentation, and after that we are going to list down all these publications which is in my PhD. So basically in this this presentation is from my it's my PhD presentation, and it's like that I have 3 or 4 papers, and which is actually I'm going to tell you about in this presentation, right? So first of all, what is crisis in cosmology? But before I'm going to talk about current crisis in cosmology, I'm going to first start that our universe is dominating with dark energy, and around the 1990s and later on 2000, it has been established that our universe is basically accelerating, and the cause of this acceleration is some kind of cosmological constant. So during 1998, the first evidence has come from the analyzing of supernovae, from where it has been observed that our universe is accelerating. Later on, so many other sources have also verified the fact that our universe is basically accelerating, and the cause is kind of cosmological constant. So in total, our universe has some dominant with some kind of dark energy, which is made of some cosmological constant. We still don't know what is this. 70% of this dark energy, 70% is the constitution of this dark energy, and then 26% is dark matter. Again, these in total we can call it the dark sectors, which is we don't know anything about, except the gravitational signature. We don't know anything. We don't have any clue of this dark energy in dark matter. And rest 5%, 4 to 5% is a normal matter, which is also called a baryon matter, in which it is electromagnetically positive. What is the meaning of electromagnetically positive? Means that it is radiating. It can be have visible spectrum. We can analyze it. We are actually made up of. So that's why we are labeling it as a baryonic matter. So the observations tells us that the lambda CDM model is kind of is considered to be a standard model to describe the cosmology at largest scale. So what is this lambda? Lambda is for dark energy and CDM for the dark matter. So from the observation, it has been found that the pressure exerted by this cosmological constant is negative, is have negative effect, so that we can have the repulsion kind of effect, and because of this negative pressure, the universe appears to be accelerating. And on the other hand, we have this cold dark matter which is present around the galaxies and all this thing, which is actually required for the structure formation, and which is found to be pressureless. And there is one more interesting feature that came out from this observation, that the universe at the larger scale is appeared to be homogeneous, isotropic, and flat. It means that the curvature of the universe is appeared to be flat. And secondly, it is homogeneous and isotropic. It means that no matter where you see the universe from here, the universe is appear to be same and all over direction. There is no any special point in the universe. Now, if you want to understand mathematically, so mathematically this can be understand, these homogeneous, isotropy, and flat can be encapsulated using the Friedmann-Lemaitre-Robertson metric, which is actually the metric in which we have the cosmic time, and we have the position, we have the coordinate, and this a is the scale factor, that how the universe is scaling up. So universe is, as the time grows, it becomes bigger and bigger. And in order to understand the expansion of the universe, we define some Hubble parameter or Hubble velocity parameter, which is basically the dA over dt, which is the change in scale factor with time over the a. And then if I say that there is a lambda CDA model, so we can model this cosmological constant as something kind of cosmic fluid. So in some case, cosmic fluid with the negative pressure, and which have energy density to be lambda just. So first of all, we can understand this constitution from the axiom. Thus the first way can write that there is an Einstein-Hilbert axiom, which is in the left side. You can see over here that R is a Ricci scalar, and square root of minus G is the metric, and then SM, whatever the constitution of this universe is, we can simply add. So this simple addition of the matter in this axiom is called the minimal coupling framework, right? So in this way, so what happens is that you have a curvature of a curvature which is actually giving you the effect of gravity, and you are just giving some matter onto it. So the thing is that they are gravitationally talking, but these matter components are not talking to each other. So this kind of adding something is called a minimal kind of effect. Now if you take a variation of this axiom, so when we are writing the axiom, we can always take a variation. So if you take a variation of axiom with respect to G mu nu, which is a metric, then we can end up with the Einstein field equation, which is shown to be R mu nu, which is a Riemann tensor, and minus of G mu nu, which is Ricci scalar, and is equal to the stress tensor. So what Einstein did, the Einstein unify the curvature with the matter energy tensor. So it simply says that you have the curvature and we have the matter energy. So matter energy tells that how the curvature will curve, and the curvature and the curvedness of this curvature will tell the matter how to move. So in some sense, they are complementing each other. So in total, they will decide how the universe will actually dominate, right? So that's why in order to have some acceleration, you must have the T mu nu such that the curvature is appear to be expanding or accelerating. So now if you solve this field equation in the FLRW metric, then we have this analytical, we can get analytic solution. So there are Friedman equation, which is 3h squared, and the next one is 2s dot plus 3h squared. So the 3h squared is called the first Friedman equation, in which the Hubble parameter is basically proportional to the energy density of the universe, right? So in total, suppose that the universe is filled with the radiation fluid, which is rho r, the matter fluid, matter density, which is rho m, and there's some kind of cosmological constant lambda. So if we incorporate these three things, then in total it will give us the rho total. And similarly, we have the Hubble acceleration plus 3h square is equal to the negative of the whole pressure. So if I just express in terms of scale factor, then we are getting that a double dot, which if the universe is accelerating, then a double dot has to be positive. Therefore we got the condition that the pressure must be lesser than -1/3. So as we are getting the observations, we understand that this pressure has to be between -1 to -1/3. So if you just p total over rho total, then we can end up with the equation of state, and this equation of state must lie between -1 to -1/3. So if you take a cosmological constant, then whose energy density is always -1, so it satisfies number of observations. Now in this minimal coupling, what happens is that all the matter components are basically conserved, which is rho dot is telling you that how the energy density of the constitution are actually varying with time. So it happens that if you add the matters minimally, then all the energy energy momentum tensor of those constituents are basically conserved. Now, although lambda CDA model is satisfied a lot of data, a lot of observation, but it having some kind of theoretical issue. People try to understand the origination of the cosmological constant. What could it be? So, quantum field theory is one of the best pillar to understand the quantum mechanics, and people understood that lambda could be some kind of vacuum energy. And when people have calculated this vacuum energy, and when they are tried to match up with the observational constraint, then it found that there is a discrepancy in the magnitude which is up to order of 120. So it cannot be possible. So rho lambda is found to be extremely small, and people have till now people do not have any kind of rigorous explanation of this kind of discrepancy. And secondly, why we have this acceleration now? Why it has not accelerated before? When we intelligent life has hit, and then this acceleration has started. So why there was no any acceleration before? So that is called a cosmic coincidence. That's why this dark energy density is actually equal to the matter density, but why it had occurred now. So there are a lot of different ways to answer it, but there is no any satisfactory explanation. Although I have to stress that the number of observations has been satisfied by lambda CDM model. So that's why people used to people whatever people are doing, people are studying with lambda CDM model. So now recently what happens is that first of all, the universe is accelerating, appears to be accelerating. It came out during 2000, and later on so many observations from the cosmic microwave background and the local distance ladder. So local distance ladder is that when you are measuring the supernova, so in the low redshift we are calling it the local distance ladder. So in local distance ladder you are measuring Cepheid variables or supernova, and you try to measure this Hubble constant. On the other hand, when you have CMB, like the photons from the early universe, so when the universe was radiation phase, and when the universe was expanding, because of this expansion the universe cooled down, and the as a whole, when the temperature has dropped out, so what happens is that the photons has no more energy to ionize the hydrogen atom. So now photons is kind of the universe become transparent, and photons have streamed from that time. So those photons are called relic photons. So those photons are actually we can observe in the in today's telescope, radio telescopes. So these are called the cosmic microwave background radiations and all these things. So in the blue we can see the we can have cosmic microwave background measurement. So it is called indirect measurement, where you have to choose some model. So in this case we have choosing the lambda CDM model, and for the supernova from the local distance ladder we are trying to measure directly we are measuring the Hubble constant. So in those two things you can see that up to 2010 the data shows that there is no much discrepancy, but after recently released Planck 2015 data and 2020 data, and the local distance measurement has huge discrepancy in the value of H0. So from CMB it is appearing that the Hubble constant is appearing to be 67 to 68 kilometer per second per megaparsec. On the other hand, if you take the local distance measurement, it's appearing to be like 74 kilometer per second per megaparsec. So this discrepancy is huge, and this is basically challenging this standard model of cosmology. That, okay, we have to think beyond, we have to go beyond this lambda CDM cosmology. Something is new. People have already thought that okay, this discrepancy might be because of the systematics, and now people have handled at a very amazing in accuracy that okay, there are it's basically real, and it is not getting it down. So you can see from the error bar that how sensitive we are getting the data. But the thing is that it is actually saying that we have to think beyond lambda CDM models. So what kind of alternatives we can think? So people have already, theorists have already proposed a lot of alternatives. For example, early dark energy. There could be some early dark energy during the radiation epoch. So when the radiation epoch was ending, so at the moment when there is a radiation density and matter density equality, there could be some peak of early dark energy. And what does it do? It just accelerate the universe, so that the Hubble value can increase if we are measuring the Hubble constant from from the CMP, right? Similarly, there could be some extra degrees of freedom due to dark radiation. It will have some additional degrees of freedom, and then it might might be some kind of solutions which can elevate the Hubble constant. Similarly, if we can have the dynamical dark energy, since you can see that the lambda CDM cosmology, we have the pressure is equal to minus of energy density minus of lambda. So what happens is that the equation of state P by rho is basically constant. So we can have more interesting expansion. For an example, we can take the equation of state, and we can expand it in terms of redshift or scale factor, and thus we can have different type of dark energy situations, right? And from the quantum field theory approach, there is a running vacuum model, so it could be treated as an alternative of well, lambda CDM model, and it may alleviate this lambda CDM. So on the other hand, so these are the alternatives which is involving changing the modifications in the matter sector. On the other hand, we can also change the gravity. So in the Einstein's equation, we have the connection which is basically symmetric. So we can modify the gravity in such a way that in teleparallel gravity or FQ gravity, there are some analysis have been done which shows that the Hubble tension can be elevated in these things, and in the end we have interacting dark matter, dark energy. So the problem is that we have to look beyond lambda CD model, and in this sector, dark matter, dark energy, which is very unknown to us, there could be some kind of non-gravitational interaction can happen, and which may increase the Hubble rate during the very early epoch, and then that's why the whole evolution of universe may change because of the interaction, and it could change, it could elevate some kind of tension. And recently what happens is that in this paper, it has been shown that some kind of model can elevate when they have analyzed this CMB using Planck 2018 data, which is approximately one sigma model. So the first of all, we have to talk about it, what is basically interacting dark energy. So when we are actually adding some matter, and so what happens is that this matter is individually conserved. So the thing is that del mu, the covariant derivative of this matter sector or dark energy sector, is individually zero, as we can see. So there is no any q newtons and minus q newtons. Now, when we are trying to understand the interaction between this dark matter and dark energy, what happens is that okay, the thing is that the interaction cannot increase, or it may change the number density also in the in the dark matter sector and so on, right? But the problem is that we don't know for sure. So for example, what we can do is that okay, so we can somehow propagate the energy from dark energy to dark matter, or dark matter to dark energy. So what we can do is, the very simplest thing is the modification of energy momentum tensor in such a way that we can add one term over here, and dark energy we can subtract over here. So in total, what happens is that our total energy momentum tensor is actually conserved. So we have to think about the total. We don't consider now that what is actually individually they are doing. So if we are writing in terms of FLRW, we can write that rho m dot plus 3h rho m is equal to q rho dot de plus 3h rho de plus p de is equal to minus of q, right? So what happens is that if q is basically your positive, so if q is positive, then the dark energy is releasing its energy to dark matter, and the vice versa. So now what happens is that somebody has taken Valentino et al. And their collaboration has taken during like 2020. So they have chosen some model like Chi is some kind of constant, and the dark energy proportional to dark energy, and the Hubble parameter, and then try to analyze this model with the Planck data, and they found that they have increased the value of H0 by several factor, which was not possible in lambda CD model. So H0 is coming out to be 72.80, which is approximately like 1.4 sigma level. So they have extremely elevated this tensor. So that's why people have now more interested in this interacting dark energy thing. And the Chi is coming out to minus, which shows that the actual dark matter is releasing some energy to dark matter is releasing some energy to dark energy. So why this happened? It says that before, during the early time, if dark matter and dark energy are actually interacting, so what happens is that it forces to release the energy from dark matter to dark energy. So what happens is that your Hubble expansion, because now if the dark energy is getting some energy, then what happens that it can raise the expansion. It can end up so the radiation era can end up quickly. So that's how it is elevating the tension in some way, right? But the problem is that when we try to understand this theoretically, so the problem with the interaction is that it has, although it is satisfactory, but theoretically it has a lot of problem. The problem is that so many people have studied this kind of things using the manual manipulation. The manual manipulation is that interaction could be, in general, interaction is morely depend on energy density or the Hubble parameter. So it has actually lack of generalization that how we can choose this kind of interaction, what is the motivation behind it. Similarly, the one of the questions that arises is that, okay, what is the your physical motivation to choosing such kind of interaction, and why in interaction there is appearing a Hubble parameter? Since you understand that this Hubble parameter is a global kind of parameter, and when you're talking about the interaction is kind of very local phenomenon, because it is happening around at a specific time. So Hubble parameter is very global phenomenon. So how you can incorporate this one? So there is no too much explanation for it. And again, when you are doing some perturbation around this kind of phenomena, then what happens is that you have to again do a lot of manipulation to handle those instabilities, because again, when you do the q plus delta q, there are a lot of instabilities, and when you have to manually fix those instabilities so that your model is making some sense. Right. So the thing is that since we do not have any microscopic theory of dark matter or dark energy, so what we can understand that, okay, we still cannot sure that how this interaction can happen. But classically, we can understand, just like in particle physics, suppose you have the two psi or phi, matter. So we can have interaction. So we can always write psi, phi, and all these things. So similarly, we have GR, general relativity, and then dark matter field and dark energy field. And so we are proposing that some kind of interaction is there, which is actually having some functional form of psi and phi. So what happens is that if you take a variation of this action, we can have the Friedman equation gets changed, because now you can see that there is additional term like rho interaction, and there is a p interaction, all these things. Now if you vary the energy momentum tensor from here, you can see that this rho m dot in the matter sector, the continuity equation, we having qm term. In the dark energy sector, we have qde term, and now they are not negative to each other. So the problem is that, okay, we require in order to solve this thing, we require the third equation. The third equation is coming from some continuity equation from the L interaction, because in total the total constitution have to be conserved. Therefore, the interaction is given by like this. So this is it. But the problem is that, okay, can we trust this kind of framework? That is, this framework have some equivalence with the former framework? So in the former picture, what happens is that we have the two things, because if you just change the continuity equation, you are not changing anything else. So you are changing the continuity equation. Your Friedman equation have the two constituents, dark matter and dark energy, pressure and pressure from dark energy. On the other hand, your Lagrangian, in the Lagrangian picture, we have the additional rho interaction and p interaction. We say that in both the picture, the dark matter and dark energy is kind of degenerate effect. Means that we cannot just specifically say that this is dark matter and this is dark energy, right? So the thing is that they are actually both working together. We cannot have any differentiation, because we have not still detected any dark matter. So we say that the both picture can have some equivalence if we say that the in both the picture the rho total has to be invariant. So if you do any such transformation between these things, let us say that rho m has to be equal to whatever the rho m plus rho d plus rho interaction, right? So if you do such kind of transformation which does not change the rho total in any phase, then we can say that, okay, these two pictures are equivalent. So can we get the in conventional picture we have rho m plus 3h plus rho m is equal to q. So from these two things, can we get something? So if we do some linear transformation, and we found that actually they are at least at the continuity level, they are basically giving us the equivalent picture. On the other hand, it is more generalized. The Lagrangian framework is having due to this Lagrangian framework, we have this the Friedman equation has changed, and the thing is that the interaction parameter has now become more generalized, more restricted. We cannot just arbitrarily choose anything. So we can study this in a very realistic form. Suppose that we have an action. The first term of this action, we can see that GR. Now for the dark matter thing, we can use the action for the relativistic fluid. So it is not it is just a relativistic fluid where you can model your dark matter, and it is found that dark matter has to be the pressureless, and as well as it is more or less it does not have any viscosity and so on. So we can analyze this one as a as a action for this fluid. So this relativistic fluid have a component of rho, which is it denotes the energy density of the fluid depending on the number density and the entropy per particle, and plus the flux density. The flux density is basically contracting with the phi and then s theta. So these phi, theta, beta, and alpha are the Lagrange multipliers, which can have different physical meaning. We will see in a minute. And then we have the field, because we require some candidate. Since we cannot just take a lambda CD model, and we want very dynamical effect and we have, there are a lot of problems associated with lambda CDM model. So we can say that, okay, we can just throw away the lambda CDM model. We can work with some kind of scalar fields. So we are choosing some kind of generalized non-canonical kind of field like Lagrangian, which is having the phi and x is coming out to be the phi dot square by 2, which is basically telling you about the kinetic energy part. If you understand in terms of quintessence, this is kind of kinetic energy part. So this is, you can say that a kinetic type of field, and we have two type of interaction. First of all, let us try to construct the interaction where we have the n comma s, which is n comma s, and then the metric and the field constitution phi comma x, right? And in the second one, we have the derivative interaction where f addition to this f, we have the flux density, and which is actually contracting with the field velocity, right? And in the later on, we are seeing there is a conformal coupling, that okay, we have the interaction and there is a direct interaction is happening, which we have already seen in kinetic and derivative case. But can this interaction also couple with the Ricci scalar, or can this interaction also coupled with a different form of it can modify the GR sector, right? So we want to also investigate those things, because in the absence of the perfect knowledge of dark matter and dark energy, we can formulate our framework in such a way that it may have some effect in the structure formation, and the validity of these models can be checked in the light of cosmological observations, right? So now, in order to understand what could be these, relativistic fluid, what is the phi and theta, we can, use the thermodynamical first law, relations, where D is the energy T ds minus P dV. And from here, we can, just do the algebra, and you can say that, okay, the temperature is corresponding to d rho by ds, and chemical potential is corresponding to mu is equal to d rho by dn. So now, if we try to vary our, action with respect to some thermodynamical quantity of J mu, so S, in case of in alpha d is equal to 0, it means that we are only taking a kinetic coupling. So the thing is, I want to clear that when we are analyzing the interaction, we are going to take at a time at one interaction. For example, we are talking about kinetic, therefore all the interaction are absent. So similarly for other ones and so on. So alpha d is equal to 0 is says that we are just only working with the kinetic interaction, and the rest two interaction are 0. So we can see that this d rho by dn, which is actually telling us about the chemical potential of dark matter, is now have been modified because of this f variable over here. Now similarly, we have the entropy. So if we vary our action with respect to the entropy, so we have this temperature of the dark matter fluid, which is again the very modified because of the dfc over ds, and this theta, we can understand this theta to be temperature gradient. Similarly, for the conformal coupling, you can see that if we vary this action, we have this df by dn with the multiplication of the curvature. So the thing is that as you are modifying your f, the things are going to be changed accordingly. But if you take now, since if you are seeing that kinetic derivative and conformal case, in this case we don't have word phi or alpha and something. So if you take the action and you vary this with respect to phi or theta, or let us say beta alpha or alpha, so it does not depend on what kind of interaction you are. So just a basic thing is that we require from this observation, we require from the lambda CDM cosmology, we require that n dot plus 3 nh is equal to 0, and the evolution is take place adiabatically, means that there is no any production of entropy. The entropy is assumed to be constant as the universe is propagating, right? So in order to understand the the playground of the field in terms of field, which fields should we talk about. So we, in this study, we have taken the K-sense field, and for the conformal part we have taken the quintessence field, which has some kind of reason we'll talk about in a minute. So first of all, if you see the K-sense field, the K-sense field has some kind of non-canonical kind of structure where there is a potential and it is multiplying with a kinetic function. So potential that is usually taken for the K-sense field is one inverse square type of potential, and here we have kinetic part, which is minus x plus x squared. So this kind of combination can actually produce the acceleration during the late time epoch if it is minimally coupled. So the energy density and the pressure is, in this field, the pressure is basically the Lagrangian of the K-sense. On the other hand, we can have the equation of the state, which is defined as the p phi over phi, which is independent of the potential. So this kinetic K-sense is basically kinetically driven. It does not depend on too much on the potential, and so on. So similarly, the sound speed. Now, sound speed is actually denoting the how the pressure perturbation is traveling on some kind of medium. For example, the medium is now Cason's field. So how the pressure is changing with respect to the change in the density. So this sound speed must be between 0 to 1. So it should not violate the causality, and this sound speed cannot be negative. Otherwise, it will have some effect, some instability in the perturbation level. On the other hand, the simple scalar field is kind of quintessential scalar field. So epsilon is some kind of triggering, where if epsilon is equal to -1, then we are going to have we will be having the phantom kind of thing. We will be having some phantom kind of thing, right? And epsilon is negative, then we will have the phantom kind of field, and epsilon is equal to positive, then we would have the normal conditions field. So phantom field is having like equation of state is lesser than -1. So now we have this v phi, and v phi is coming out to be v naught e to the power lambda, so exponential type. So these potential, people have already studied the quintessence field around, using the exponential potential, because of, again, it has rich state from the particle physics, and that's why people have studied this one. And now this type quintessence field is heavily depending on the potential. Now you can see the equation of the state of this field is x minus v and x plus v. In order to have the accelerating effect, the v should be greater than the x. So x is basically denoting the kinetic part. So the potential energy is playing a role leading to the accelerating epoch, right? And similarly, the sound speed, if you take the variation with respect to dp over dx, it is always coming out to be unity. So unlike the Cason's case, it is always 1. In the Cason's, it is a kind of a variable, and it can be negative in some cases, it can be positive, and all these things. So therefore, what could be the so if we try to see the space-time dynamics, because what we are interested, we are not interested in thermodynamical case. We can analyze the rho interaction part, p interaction part, if we just choose to compare it from the perfect fluid. Let us say we have a stress tensor for perfect fluid, which is given by rho plus p u mu. U mu is the velocity of the fluid, and the pressure is g mu nu. When we are going to compare it, so we can analyze for the different part of the matter and the interaction and all these things. We can from there compare that, okay, this is the pressure and this energy density, and we can obtain the field equation from this action just by delta phi is equal to 0, so varying the action with respect to phi. And similarly, if you find, we can easily obtain the continuity equation with some algebraic manipulation. And for the kinetic case, the q0 is coming is depending on the derivatives with respect to phi field and the x field and the phi and x. So in this case, when the kinetic coupling case, the interaction function is basically the derivative of the fields and all these things. On the other hand, if you see the derivative coupling, in this coupling, we have this additional h, and this additional h is due to the factor of this j mu, which is basically the particle flux density. It's basically contracting with the velocity, which is actually responsible for appearing the h in this one. So since we have no since it's again that we are trying to construct an interaction as generalized as possible. So if we have this kind of thing, we can have this kind of thing. And now if we have our fundamental approach that, okay, we have action, and now if you try to study in the perturbation, then there will be no instability. Like, we do not have to manipulate something by hand. Everything is consistently will be fixed from this approach. So now in this case also, the total moment energy is conserved, and so these are the field equations in the case of kinetic coupling and derivative coupling. It's look very complex and all these things. So how we can understand, how we can check the viability of the models that we have worked out. So for that, we want to understand the qualitative behavior of the model that we are going to propose. So how we are going to understand dynamic qualitative behavior of the models that we have already proposed. So in this case, what we have to do, we can see over here that these phi double dot and all these things, they are signifying the second derivative. So what we can do, that we are, first of all, we have to choose some dimensionless variables. So what are the number of dimensionless variable is required to systematically express the whole system into the first differential equations. So that is our job. So we have to choose the dimensionless variables in such a way that we can convert this second order differential equation into the first order differential equation. So our primary variables are x, y, and z, and we can, using some equations, we can express the sigma. Sigma is over here the fluid density. So using the Friedman constant relation, Friedman equation, first Friedman equation, we can express sigma square in terms of the other variables like x, y, and z. Omega phi is given as the field density, and the field density can also express in terms of x and y. Similarly, we have slope, and for the inverse square law of type of slope, then we have the lambda. Now, in some sense, if you have additional parameter, right? So for that additional parameter, if it is left out, you cannot express those things in terms of your presumed variables. So what you have to do, you have to additionally define the new variables and then systematically construct your differential equations and all those things, right? So over here, if we use the kinetic coupling, so we have the z square is equal, z is equal to kappa square fc over 3h square, and for the derivative case, we have to multiply with an FD, right? So we have this Friedman equation, and from the Friedman equation, we can analyze the sigma square, and the sigma square has to be between 0 to 1 because it's again denoting the fluid density, and the fluid density is, from the analysis of the minimally coupled scenario, that we can understand that any physical constitution cannot have the negative energy density, right? So after that, when we have already selected our primary variables like x, y, and z, our primary variables, then we have to construct an autonomous system. So we can take a time derivative of dx by dt and again express. And again, we can find that phi double dot. In this case, x dot is equal to phi double dot. So from the field equation, we can express everything in terms of y and z. And similarly, so a becomes some function of x, y, and z. Similarly, y prime and z prime. So these a, b, c, they will not explicitly depend on time. So they are completely independent of time. So after that, we have to find out the critical points. What are the critical points? They are also called the stationary point. And around these points, we have to find out that what kind of what is the basically qualitative behavior of the system around those critical points. And then we are going to find out the stability, because the stability is much more important than how our model is actually physically viable or not. So what we, in order to find the stability, what we have to do, that we have to linearize this autonomous equation. The meaning of linearization is that we have to first a, b, and c, we have to do the Taylor series expansion around the critical points, so that we have having the Jacobian matrix, and then we are getting the eigenvalues, and based on the signature of the real part of these eigenvalues, we are going to comment that, okay, if the real part is coming out totally positive, then this critical point is unstable. For negative sign, it is stable, and if we have the alternate sign, then it is coming out to be saddle, right? So, and on the other hand, when we have so this is all about the stability. Now beside the stability, we require one additional things, like, so the critical points, are solely stable, are they accelerating or non-accelerating? Because some of the critical points can exhibit accelerating solutions. Some of the critical points cannot be accelerating, or it is required, because our universe, we understand that our universe has gone through multiple epochs. First it was radiation dominated, then it is matter dominated, and now it is in accelerating phase. So the critical points, because in our system, if you are taking different constitutions, for example, we have standard gravity, we have the dark matter fluid, we have the field, we have the some interactions. So the field is responsible for dark energy kind of signature. So we must produce the systematically that some of the critical points should be towards non-accelerating solutions, some of the points towards accelerating solutions. And so we are actually we are stick with the omega total, because now our whole system is now becoming as a total system, because everything is intact, and so we cannot just see individually. So omega total is defined as p total over rho total, or if you describe in terms of Hubble parameter, is the solution. So that's why, if omega total is between 0 to 1 by 3, we can say that it is a non-accelerating solution. If it is lying between -1 to -1 by 3, we can label it as an accelerating solution, which is required. And omega total is lesser than -1, which is known as a phantom solution. On the other hand, similarly, since we are taking as a one system, we can generalize the sound speed to the total system, which is actually can be between 0 to 1. Okay. So now we have constructed a model. We cannot construct as large as possible. So we have confined ourselves so that the dimensionality of the autonomous system is not increasing, right? So if our autonomous system is increasing, then it is what happens that the phase space associated with the autonomous system is also increasing. So if up to 3 dimension we can easily study, although it will affect that. Okay, the sometimes the phase space can become what do you call, what you can say, the phase space can become non-compact, right? So the thing is that we have to take care of all these critical points at infinity and all these things. So that is the problem with these kind of with these things. So we have to choose, we have to construct our interacting model in such a way that the dimensionality of interaction is not violated. Similarly, the FC has the dimension of m to the power 4, so we cannot just simply choose that okay, this has to be rho and something. It is properly dimension, it respecting the dimension, and also it is with that it is follow also the Lagrangian, so we cannot just choose a rho plus something and something. So these are the proper constant that we have to see. So we have chosen something like exponential type of interaction where e to the power beta x phi over kappa to the power m, because phi is normalized with kappa to the power m, then rho to the power epsilon. So now we have very complex field equation, and this there is a complex parameter space, the parameter space which is basically epsilon, m, and beta, and there is a potential parameter which is coming out to be delta, right? So what we can first do, that we have obtained the critical points, and for all these critical points we are choosing those critical points first of all, for which the interaction parameter, which is basically z, is not equal to 0. So because we require that the interaction, the whatever the critical point, it must have it has to be it must contain the interaction, otherwise there is no point, because if that is equal to 0 there is no interaction, and all the things are equal to 0. So the thing is that therefore we have taken those critical points and try to find out what is the omega total. And in the green region it shows that the accelerating region, in the bluish region we have taken it to be phantom region. So when we have put the critical points in omega total, then we have found that it is just only depending on m and epsilon, and the other parameters like beta and delta are absent. So it is constraining m and epsilon, and the other and we have to put again different constants. Now for example, if you want to linearize the autonomous system and try to find out the eigenvalues corresponding to each critical points, then we have said that this is very complex and we cannot do it without going to the numerical state. Analytically it is not possible. So what we can do, we can choose the coordinates of m and epsilon, which is maybe in the green region and also in the bluish region. So what we have found that if we choose any coordinate which is lying bit in the blue region, then the sound speed becomes negative. So it says that your system has become now phantom, because epsilon m, bluish region, is phantom. So phantom can be stable. The eigenvalues we have found is to be negative, all the eigenvalues are negative, but it is not producing any positive cs square, the positive sound speed square, right? So if we have abandoned those models, because we understand that if cs square is negative, then it will eventually produce instability at the perturbation level. So if you are working with the CMB data and these things, you do not want any kind of instability in your theory, right? So what we can do is that we are choosing that, okay, if any critical point which is actually producing the accelerating solution, then we must understand that, okay, the field is basically dominating, right? So we are not saying that the field has to be in a completely point of one. So the field and the interaction is playing role, and the fluid is basically subdominant. The dark matter fluid has to be subdominant. So we found this if we are choosing some of the epsilon to m. So over here we have chosen epsilon to be 0.1 and m to be minus 0.1. So we have considered a space where we have the green region to be the green region for the eigenvalues, and this gray part is for this omega phi between 0.65 to sound speed 0 to 1. So we have seen the overlapping region over here for the 15 to 20, and beta to beta is in this case has to be negative, and little bit I think positive, right? So this is this is the case. So in order to understand, in order to construct the free space, what we have to do, because now x can take any value from minus infinity because it is the velocity. Similarly, y can also take from 0 to infinity because it's a potential, it cannot be negative. And similarly, the interaction is not bound, because that is the problem with when you're talking about when you're working with the three-dimensional autonomous system. So everything becomes non-compact. So we have to scan all the phase space from minus infinity to infinity. But thanks to some kind of autonomous system over here, that y cannot go to minus infinity to infinity, because it is simply behaving as symmetric. And over here we have also some kind of symmetry in the z in the autonomous system. So again we can just seek with the critical points at positive infinity or negative infinity, right? So we have chosen the benchmark point epsilon to be minus 0.1 and to be minus 0.1, and some delta to be 20, beta minus 1, and alpha c. Either you take minus 1 or plus 1, does not have any effect. And we have found 1, 2, 3, or 5 critical points. A3 is kind of, it is lying in the negative x-axis, and it is showing the, phantom type of solutions. So any trajectory which is actually originating there, it is ending up with A3, and A3 is non-interacting point. So Z is becoming 0. So it is not giving us any kind of very interesting signature. On the other hand, if we are talking about the accelerating regime, then we have seen that A2, A4, and A5 are A5 is just only the accelerating critical point where non-zero is at. On the other hand, there is no trajectories going through A2. So since we are talking from X to Z, so because at A2 the fluid density gets violated, so there is no trajectories going from A2. And then we have A1 where simply x and y everything becomes I guess 0, and z is only dominating. So again it's appeared that some trajectory can go towards it. And A5 is basically giving us the global stable critical point, because everything each and every critical point trajectories orbits are actually all attracted towards A5. So in this case we are getting accelerating solution, and it will be very visible if you are plotting the evolution of these cosmological parameters. Let us say, for example, omega phi is giving us the and the fraction density of the field, and similarly we have the sigma square, the fluid density. Omega total is the equation of state and sound speed. So we see that the KSNs have a funny feature. If we do not have any radiation fluid in our system, but KSNs have the property that it can behave like radiation in the early epoch in the presence of the 1 by phi square type of potential. So we can see that KSNs is basically dominating the very early phase, and the omega total is about to be 1 by 3. So in that scenario, we can say that okay, this is a radiation kind of epoch, and at that moment, the sigma is the fluid density is nevertheless 0. So as we are progressing towards the matter epoch, sigma square is dominating, K essence is basically decreasing. So since it cannot cannot act like dark matter, so that's why we are seeing that the energy density is basically decreasing. And as we are approaching towards the present moment, present time, we are seeing that the cases is basically increasing, and dark matter is actually going down. It's about to be 0.3, and case intensity is about to be 0.7. So the thing is that if we are choosing the K-essence field, it is more dynamic. It is showing the more dynamical feature, and the thing is that now, since KSN has shown this type of behavior for wide class of or wide range of wide array of initial conditions, so we can say that at some degree we can say that it is also was addressing the problem of cosmological coincidence, right? And during the whole evolution, the sound speed is between 0 to 1. Right. So, and we can see that the omega phi is basically is saturating towards like 0.7 to 0.8, and the sigma is with the fluid density is actually diluting, and whatever is absent is just omega interaction. So we do not have to consider that thing. Now, similarly, for the derivative effect, we can do the following, and we have seen that the beta and delta have some kind of constraint for that kind of thing. And over here, the dimensionality of FD is proportional to M, so that's why it has some different kind of parameter constraint. And again, similarly, we have like A4, A1, A2, A5. Yeah, in this case, A5 is the accelerating solution over, and A3 is again the phantom kind of solution, the similar behavior. And again, here we can see that at the very late time epoch, the dark energy density is basically dominating, and the equation of the state is the total equation of the state is converging towards like minus 0.678, minus 0.89, right? So In that case, the evolution, the background evolution is nearly same. So one can do some different analysis, for example cosmological perturbation analysis, and then they can see the effect, that what kind of effect it can have in the structure during the structure formation. Now come to the conformal coupling. So because of the conformal coupling, the field equation has now have some contribution of R, which is visible from here, and the Friedman equation has now becoming different. So we have just rho m and rho m and rho phi, but the whole the Friedman equation has changed, and some kind of a derivative of f is appearing, and the symbol is, because of this thing, the Euro standard general relativity has now modified. But we can say that it follows the Bianchi identity. It says that the covariant derivative of Einstein tensor has to be 0. So we can redefine our energy momentum tensor with these definitions, T mu1 and T mu2, and we are expecting that okay, the covariant derivative has to be 0, so we can get additional constraint from there. And again, in order to understand the dynamical analysis, we are just changing, because we are using just only in this case we are using the quintessence field, because x has phi dot, and when we are taking the derivatives, it will again take a lot of other derivatives. So there is some kind of problem which we are going to address in recent time. So x is basically defined as phi dot, and it is normalized with the Hubble parameter. Similarly, y is not changing. Sigma has same thing, and z is for over here, because it is coupling with r by 2 pi square. So z f becomes just like a free variable. So z is f, and omega phi the field density, which is normalized with Hubble parameter, and lambda is the slope of potential, which is having, we are using the same definitions, the standard definitions, and we have getting the constant equation from the Friedman equation, first Friedman equation, and we are using the quintessence potential to be exponential type. So over here, the model that we are working with, again, exponential type of a thing, because it has, in the Friedman equation, we have f comma phi. Either you can choose f to be proportional to phi, or we can have this e to the power gamma phi, so that we will not get any additional parameter, and thus we do not require any other additional parameter to capture those get those things. So therefore we are restricted that our autonomous system must be in the three-dimensional, and we do not want to complex too much. Now getting the critical points is tricky situation over here, so we are not going to in that in a very detail. So numerically, we have found explicitly that there are some techniques from which we have found that okay, these kind of parameter space for which we can have the accelerating solution, where it is showing that omega total is kind of minus 0.87, and corresponding the field density is 0.74. So we have this omega phi, which is basically x squared plus y squared. So it is a very nice symmetric one. So it has to be between 0 to 1. And again, we have specified while obtaining the critical point, we have said that okay, this whatever the critical point must be, z should not be 0 over there, and the omega phi is kind of greater than, let us say, 0.5 and so on, right? So we are expecting, so z is equal to tan inverse of z. So we have this x, y, and z situation over here, and we are seeing the trajectory originating from P2 as actually converting towards P6, and P6 are our accelerating situations. So some trajectories are originating from z is equal to pi over 2, and they are also converging towards P towards 6. So so P6 becomes a global accelerating solution, stabilization solution, and if you are trying to evaluate find out the evolution of the system, we are seeing that as usual, the quintessence, when the z is equal to 0, the quintessence have in the past epoch, the kinetic energy of the quintessence field is dominating, and the matter density is approximately 0. But the interesting thing happens between -1 to -2 to -0, that during the matter phase, the field density is no longer 0. Right, so it has very advantage in can be seen in case of in case of structure formation, that structure formation, or maybe in the early type of formation, late time non-linear large scale structure formation. So, and after that the fluid density is basically converging towards 0.3, and 0.3, and omega phi is nearly converges towards 0.7, and omega total is converging towards -0.8. So if we choose some different benchmark points, then we can get up to minus 0. Minus up to -1. So it depending on that how well you are going to custom these variables. So the test is, so validity of these models can be identified when we are going to actually do the test from observational perspective. So the conclusion is that in the kinetic and derivative coupling, the coupling introduces at the Lagrangian level and generalized interaction and consistently produce the equation of motion. For these two type of couplings, the background equation is evolution is nearly same, whereas the constant of the model parameters are distinct. And the distinction between we can distinct these models based on the perturbation level, that how it is introducing some change in stress formation and all those things. And in the conformal coupling, the curvature coupling of interaction functions affect both the matter and gravitation sectors simultaneously. The model exhibit non-zero field density during the matter epoch that can affect the structure formation, and unlike the matter interaction, the fluid density does not vanish entirely during the late time epoch. So we can see, very interesting phenomena associated with kinetic and derivative coupling as well as the conformal coupling. And in the end, my publications, I have recently 7 publications up to till now. So recently, the first one is accepted in physical review D, and it has come online. Second one is again, it has published around again in October, I guess. So, and the third one is we have worked with the dynamical stability in presence of non-minimal derivative coupling solution. So it is published in the EPJC, and in another way, we have also worked in the tachyon dark energy field, where it is published in the physical review team, and we have also worked in the ghost condensate in the case of pure kinetic cases. So it's published in the universe, and the nature of cosmological perturbations, where because of the expansion of the gravity, because of the expansion with the matter particle or the pressureless particle or dark matter particle can be produced via the via the gravitational particle propagation mechanism. So we have also published in the general relativity and general relativity and general relativity and these publications, Springer publication, and then in the first publication was came for dynamical stability of the KSN's field interacting non-minimally with perfect fluid, which is around 2021, and which is based on the kinetic coupling case. So there are some few differences we can see for the model of dark matter coupled to dark energy. Nicola Tamini has shown that phenomenological models of dark energy interacting with dark matter, which is actually the equivalence between the former and later on Lagrangian interaction picture. And there is Bethoni, which is actually shown. First of all, he has shown that the interaction is basically coupling with the Ricci scalar, and then the first of all the Christian G. Boheman has worked out the interacting quintessence case from the variation approach. So I think, thank you very much for seeing my video, and hope you have liked it, hope you have understood the things, and later on we will again make different videos. So see you later on. Thank you very much. This is Cap signing out.